Good morning, students. We are going to conduct class 5 of second BSc chapter 3, that is in unit 1 groups, that is group theory. That is now we want to learn the definition of order of an element. The definition of order of an element. The order of an element A in a group G is said to be n if n is the least positive integer such that a power n is equal to e for all a belongs to G. That means the order of an element A is said to be n if n is the least positive integer such that a power n is equal to e. We simply written as order of A, O of A is equal to n. That means we can use it as, that means we can written as order of A, O of A is equal to n if and only if a power n is equal to e, where n is least positive integer, where n is, that means if a power n is equal to e, where n is least positive integer, that means if a power n is equal to e, a power m is equal to e, in both conditions, a power n is e and a power m is e, n and m are both positive integers. Then what will be the order of A? The order of A is the least positive integer. That means in both m and n, which is less integer, less quantity integer, then that is said to be order of that element A. Now we are going to the theorem number 9. That is, in a group G, if A belongs to G, then order of A is equal to order of A inverse. It means order of A is equal to order of A inverse is to prove us. For that, here is given that G dot is group, and for A belongs to G, I am taking that for A belongs. Let order of A is equal to n and order of A inverse is equal to m. I am taking that order of A is equal to n and order of A inverse is equal to m. We have to prove order of A is equal to order of A inverse. That means we have to prove this m is equal to n. Okay, order of A is equal to n. What is that? By using the definition, a power n is equal to e, and that n is the least positive integer for A. For order of A inverse is equal to m, by the definition of the order of the element, A inverse whole power m is equal to e, where m is the least positive integer in A inverse case. For the element A inverse case. Okay, right. Now, here is A power m is equal to e. I am taking both sides inverse. That is, A power n whole inverse is equal to e inverse. A power n whole inverse, for the powers are n and minus 1 are interchangeable. That means a power minus 1 whole power n. It can be written as a power n whole power minus 1 can be written as a inverse whole power n. What is E inverse? The identity inverse is also the identity. That means E inverse is equal to E. Okay, right. Here A inverse whole power n is equal to E. Here also for the element A inverse, we have A inverse whole power m is equal to E. In both cases, with the same element A inverse power n is E, A inverse power m is E. But here order of A inverse is equal to m. That means m is the least positive in A inverse powers. Okay? That means this m is less than or equal to n. M is less than or equal to n. We are taking it as 1. We have order of A inverse is equal to m. Order of A inverse is equal to m. What is the definition of order of A inverse is equal to m? A inverse whole power m is equal to e, where m is the least positive integer. Okay, right. Now I am writing both sides. I am taking both sides inverse. That means A inverse whole power m. Sorry. Now I am taking both sides inverse for this one. That is A inverse whole power m whole inverse is equal to E inverse. I am taking inverse on both sides. I am interchanging these two, minus 1 and I am interchanging this m and minus 1 whole power minus 1. That means a power m whole power minus 1 and the whole power minus 1 is as it is. Here E inverse is E inverse. We can write as it as E, no problem. We can write a power m whole inverse minus 1 into minus 1 plus 1. That means we have only a power m is here. And what is E inverse? E is the identity. E inverse is equal to E. Therefore, a power m is equal to E. But order of A is equal to n. Order of A is equal to n means a power n is equal to E and n is the least positive integer. Here also a power m is equal to E, but m is only a positive integer. That means in both cases a power n is equal to E. Here a power m is equal to E. But order of A is equal to n means n is the least positive integer. That means m is bigger one. That means n less than or equal to m is the here a power m is equal to E, a power n is equal to E. But order of A is equal to n. N means n is the least one. That means m may be bigger one when compared with n. That means n less than or equal to m. N is less than m or equal is there. You say let it be 2. From 1 and 2, from 1 here is m less than or equal to n. From 2 n less than or equal to m. That means that m is equal to n. What is m? Order of A inverse. What is n? Order of A. That means order of A is equal to order of A inverse. That was proven. Now we go to the next theorem. What is that? Theorem number 10. If A is an element in a group G such that order of A is equal to n, then a power m is equal to E if and only if n divides m. This is meaning m is strictly divided by m. N divides m means m is divided by n. The remainder where n belongs to Z plus. Here n is also a positive integer. Here this is if and only if condition, that is necessary and sufficient condition. For these necessary and sufficient condition, there is a common data is there. What is the common data given? A is an element in group G such that order of A is equal to n. Order of A is equal to n and A is an element in group G is the common data given to prove the necessary and sufficient condition in between these two. So I am writing that first given A is an element in group G such that order of A is equal to n. By the definition of order of A is equal to n, we can write as a power n is equal to E, where n is the order of A is equal to n means a power n is equal to E, and that n is the power n is the least positive integer. Okay, right. Now I am taking the necessary condition. I am going with necessary condition. What is necessary condition? We have to take LHS side. That is let a power m is equal to E. That's why I am taking that let a power m is equal to E. We have to prove that n divides m. N divides m. Okay, right. For that, m is a integer and n is a positive integer. That means n may be in denominator. By division algorithm, for m comma n is positive integer. Z plus means positive. Positive means the numbers are from 1. They are started from 1. That means there is 0 is not neither a positive nor a negative. So n must be non-zero. Okay, then there exists q comma r belongs to Z such that m is equal to nq plus r, where 0 less than equal to r less than n. This is the division algorithm. Now we have m is equal to nq plus r. I am taking these two on the a power. A power m is equal to a power nq plus r. Here we observe that a power m is equal to a power nq plus r. A power nq plus r can be divided into two parts. A power m plus n is equal to a power m into a power n. By using that condition, I am writing that a power nq plus r is into a power nq into a power r. A power nq is written as a power n whole power q. A power r is as it is. What is a power n? We have given that, we have taken that order of A is equal to 1. In the data, order of A is equal to n means a power n is equal to E. Okay. Now I am writing that a power n is equal to E. E power q, identity power anything is identity. That means e power q is equal to E. A power r is as it is. E into A power R is A power R because E is the identity element in group G. Here, A power M. What is A power M? We have taken in the necessary condition A power M is equal to E. That means LHS part becomes E and RHS part becomes E into A power R is A power R. So we got A power R is equal to E. Okay, we have here both two conditions are there. Either R is equal to 0 or 0 less than R less than N. In both cases, in these two cases, which one is right? So I am taking that, I am removing this equality and I am taking that if 0 less than R less than N here. Students kindly follow the cursor. If 0 less than R less than N, then we get the contradiction to order of A is equal to N because here A power R is equal to E and we have A power N is equal to E because order of A is equal to N means A power N is equal to E where N is the least positive integer. Here N is the least positive integer in A power C is equal to E. Here A power N is equal to E, here A power R is equal to E. In these two cases, here N is the least one. But if we observe here, there is R is the least one, which is impossible because order of A is equal to N means A power N is equal to E says that N is the least positive integer. But here R is coming. That means it is contradiction. So the only possibility is this equality, that is 0 is equal to R. That means the only possibility is R equal to 0. If we substitute here, kindly follow the cursor, that R is equal to 0 in this one, then we got M is equal to NQ. We have M is equal to NQ plus R. Is it right? What is here? The possibility is R equal to 0. If you substitute R equal to 0 here, NQ plus 0, then this, that is NQ. M is equal to NQ, where Q is an integer. That means this N divides M, or M is divided by N is equal to Q. M is divided by N is equal to Q. The cross one is the divided by symbol, and the straight line is the divides symbol. M is divided by N. If we divide M with N, we got some integer. That means N divides M. So we have proven the necessary condition. If we go to the sufficient condition, what is the sufficient condition? We have to take N divides M and we have to prove that A power M is equal to E. The common data is written here. Okay, you can observe it. Given A is an element in group G such that order of A is equal to N. Order of A is equal to N definition is A power M is equal to E and that N is the least positive integer. We have written here also. We can use this data for the sufficient condition also. To prove this sufficient condition, first I am taking that suppose N divides M. N divides M. N divides M means M is strictly divided by N. That means if M is divided by N, we got some quotient Q, where Q belongs to Z. M divided by N is equal to Q. By cross multiplication, M is equal to N will be cross multiplied with Q, NQ. Now I am taking both sides A power. That means A power M is equal to A power NQ. A power M is as it is written in the next step. A power NQ can be written as A power N whole power Q. What is A power N? The common data A power N is equal to E. So I am substituting this A power N E. E power Q. E is the identity. So E power Q is E. So A power M is equal to E, which was we want to prove in the sufficient condition. So the theorem was proved for the sufficient condition also. That means A power M is equal to E if and only if N divides M was proven. Hence, if A is an element in group G such that order of A is equal to N, then A power M is equal to E if and only if N divides M was proven where N belongs to Z. Now we go to the next theorem, theorem 11. That is, the order of an element of a finite group G is finite and is less than or equal to the order of the group. That means if we take a finite group, okay, the order in that finite group, if the order of any element in this finite group is finite, first of all, we want to prove that one. If for that I am taking that suppose G is a finite group and for A belongs to G, I am taking that by closure law in G, A belongs to G, A into A also belongs to G, because G is group, by using closure law for the single element A into A also belongs to J, and so on. A comma A into A is A square, A into A is A cube, and so on. All elements are belongs to G. I am checking that all these elements are distinct or not. I am taking that if any two elements are equal, let A power R is equal to A power S, where R is greater than S. Now I am multiplying both sides with A power minus S. A power M into A power N format. That is, what is that formula? A power M into A power N, A power M plus M. That's why A power R into A power minus S, A power R plus minus S. That means R minus S. A power S into A power minus S, A power S minus S. A power S minus S is A power 0. A power 0 is 1. That is identity E. A power R minus S is as it is. Since R greater than S, R minus S greater than 0. Therefore, there exists a positive integer R minus S, because R minus S is greater than 0 means that is a positive one. That means for R minus S is a positive integer, such that we got that A power R minus S is E. So the order of an element in a group is finite, because R minus S is a positive integer and A power R minus S is E. That means the order of this A is maybe R minus S or less. That means it is a finite one. Sorry, students. So first one was proven. That means the order of an element of a finite group is finite. We have taken a finite group G and an element A, and that element order is finite. Okay? Okay, right. Next we prove that. What is that? And onwards. Kindly check in the question, that is the statement, that is, it is less than or equal to the order of the group. That means the order of an element is less than or equal to the order of the group. So we want to prove here is order of that element A is less than or equal to order of group G. We have to prove this one. For that I am taking that order of A is equal to N and order of G is equal to M. Again by closure law, A square, A cube and all belongs to G. I am again taking that if possible that A power R is equal to A power S, where R greater than S. I am multiplying with A power minus S on both sides. That is A power R into A minus S is equal to A power S into A power minus S. A power R into A power minus S is A power R minus S. A power S into A power minus S is A power S minus S. A power S minus S is 0. A power 0 means identity, that is E. A power R minus S is equal to E. We want to prove, now we prove that order of A is less than or equal to order of G. First we prove that order of A less than or equal to order of G. We have taken that order of A is equal to N, order of G is equal to M previously, and also written the same one. All these are the same one. But R minus S is less than N, because I am taking that let A power R is equal to A power S, where 1 less than or equal to S less than or less than or equal to N. Are you observing that? I am multiplying with A power minus S on both sides. The same process gives the A power R minus S is equal to E, which we have written in the previous one also, which I have done in the previous one. But here R is the bigger one, S is the smaller one. R minus S is, these two are less than or equal to N. S is less than or equal to N, R is less than or equal to N. If R minus S means strictly less than N, is it right? But we have that order, we have taken that order of A is equal to N. Order of A is equal to N means that N is the least one. Here A power R minus S is equal to E, and that R minus S is less than N, which is contradiction to order of A is equal to N. Because A power order of A is equal to N means A power N is equal to E, where N is the least positive integer. That means N is the least positive integer where A power N is equal to E. Here also A power R minus S is equal to E, but R minus S may not be a smaller one, because order of A is equal to N means A power N is equal to E, where N is the least positive, least one. But here R minus S is the less than N is not possible. That's why any two elements in these elements, we have taken any two elements are equal, we get a contradiction for this one. So all these elements are distinct elements. That means different elements. How many elements are there? Because order of G is equal to M, that means G contains only M elements. All these are M elements. In elements, how many elements? M elements. All the elements in group G are M distinct. Distinct means different elements. Therefore, N is not greater than M. Is it right? Because the maximum elements in G is M. So N may not crosses the value of M. That means N less than or equal to M. Okay, right? That means what is N? Order of A is less than or equal to what is M? Order of G. Order of A less than or equal to order of G. Okay. Now we've proven that the order of an element is less than or equal to order of the group G. Is it right? That is the second one. The theorem was over. Students, I am posting this in your WhatsApp group in the PDF format. So write the notes and complete the notes thoroughly. Kindly follow the classes thoroughly and kindly understand that if you follow regularly and if you write notes regularly, then only you can understand the subject. So I hope you are all complete the notes earliest, and I will check those notes in the next class.